So we're just going to clean up some things today in terms of electron configurations. So why don't you pause the video and give me the full electron configurations for neon and argon. So neon, oh boy, get my periodic table out again. Neon is way over here. It has 10 electrons over here. So 10 electrons. So that's 1s2, 2s2. And then the next would be 2p and can hold up to 6, which would give us 10. That's perfect. Okay. Now argon has 18, and that's 1s2, 2s2, 2p6, 3s2, and after 3s comes the 3p, and in the 3p, let's see, we're at 2, 4, 10, 12, we need 6 more, perfect, 3p6. All right, so let's talk about this for a minute, okay? So neon and argon are both noble gases. That's anything in group 18. So helium, neon, argon, krypton, xenon, radon, and this thing that hasn't been named yet. Noble gases are very stable, and they have very stable electron configurations, okay? So if I look at these, I say, hey, look, this has a 2p6 at the end, and this has a 3p6 at the end. Okay, so it seems like the noble gases might always end in the p6, and that is correct. Okay, so what we do is we do something called noble gas notation. Okay, and noble gas notation is a bit of a shortcut, okay? So what it does is this bit here, notice how this is the same, 1s2, 2s2, 2p6, okay? So if I were to write argon in noble gas notation, what I would say is instead of writing this 1s2, 2s2, 2p6 business, if I just say that I start with the noble gas configuration of neon, which you indicate with brackets, so argon would be neon, and then I go from there, 3s2, 3p6. All right, so this is actually quite a great shortcut, and when you combine it with what I'm about to teach you, it makes doing electron configurations a snap. So let's go on to the next page. Okay, write the noble gas configuration for sodium and potassium. All right, so why don't you pause and give it a try for that. Noble gas configuration for sodium and potassium. Well, sodium is right here, so it has the same noble gas configuration as neon. So we're going to start it with neon. And then if I go back, I know that after neon, there's this 3s2. Okay, this 3s subshell. Well, actually, sodium would just have a 3s1. Okay, and potassium, would have argon. Okay, now argon got you up to 3p6, so after the 3p6 is the 4s, and it's 4s1. Well, that's interesting. So these both end in s1. These two. This is 3s1, this is 4s1. So as it turns out, every single one of this group 1 ends in s1. Oh, that's good to know. Okay, now hydrogen is 1s1, lithium is 2s1, sodium is 3s1, and potassium is 4s1. Okay, so you're getting that, hopefully you're getting that the period is the same as the shell. Okay, that's what I was hoping for there. And I could do something similar for beryllium and magnesium, but instead of S1, these would have 2 electrons in that S subshell. And in fact, these two groups right here, this is called the S block. Okay, so in the S block, the period is equal to the energy level, or the shell. Okay, so that makes it, that's nice. Okay, well, what about nitrogen? Now, I'm asking for noble gas configuration here, so nitrogen would be helium. And then after helium, we go to lithium. Now, remember that lithium is a 2s, right? This subshell that the electrons fill for lithium or beryllium are the 2s orbital, right? So it's 2s1, 2s2. Okay, so I can just kind of march across the table like that. And then I come over here, and this is 2p1, 2p2, 2p3. Okay, so what about phosphorus? Okay, well, phosphorus starts at neon, and then it goes from neon to sodium, which we already said was in the 3s, 3s2, and then we go out to phosphorus, which is 3p3. All right, now a couple things to notice here. All right, nitrogen and phosphorus both end in the p subshell. All right, well, what about boron? Well, boron would be P1. This would be 2P1. Aluminum would be 3P1. Carbon would be 2P2. Nitrogen is 2P3. Oxygen is 2P4. This is 2P5, and this is 2P6. So what we can kind of do here is we can say that this element right here is P1, and then we just kind of work our way across. So this is, all of this here is called the P block. So in the P block, the period is also equal to the energy levels. Okay, well, let's move our way down to nickel, which is right here, element number 28. So argon is the last noble gas, so I'm going to go back and I'm going to go over to argon. Okay, so here's argon. And then after argon, we go argon. Then the next element is potassium, and potassium is 1, 2, 3, 4s. 4s. And I got 2. And then I've got nickel, and nickel's got to come all the way over here. Now, okay, so argon's got 18. I did 2 more. That gives me 20 electrons. And so nickel has 28, so I need 8 more electrons. Okay, well, after the 4s2, if I look back at, if I look back here at my shortcut, after the 4s, we actually go to the 3d. Okay, so this is the D, these transition metals here, these are the D block. Okay, so in the D block, okay, wait. So let's finish nickel here. Nickel is 4s2 and then 3d. Now the D, there are, let's see, 1, 3, 5 orbitals in a D subshell. So the D can hold a maximum of 10 electrons, right? So it should be able to do this 3d8 business. That's no problem. Okay? Now, the D block, for the D block, the period or let's say the energy level, or just shell, is equal to period minus 1. Okay, so that keeps it pretty easy. And again, you do it more or less the same way. This would be 3D1, this is 3D2. I'm going to skip for a little while. This is 3D8, 3D, well, okay, copper is kind of special, but zinc is 3D10. Okay, so what about zirconium? Well, here's zirconium. Okay, so if I go up and I find my last noble gas before zirconium, that'd be krypton. So I'm going to start with krypton. And then after krypton, I go to rubidium, which is in the 1, 2, 3, 4, 5, fifth period. So that's a 5s2. And then it would go into the D block, which is 1, 2. So 2 electrons into the D block. And remember, for the D block, the shell is the period minus 1. So this is 4d2. Okay, now S block, period equals energy level. P block, period equals energy level. The D block, period equals, oh yeah, boy, period minus 1 equals the energy level. And this last little bit down here is actually called the F block. And in the F block, the shell is, hopefully you figured this out, period minus 2. So uranium, uranium, that's a big one, okay? The noble gas before uranium is actually radon. So that'd be Rn. And then after Rn, you go down here to the 1, 2, 3, 4, 5, 6, 7th period. So that's 7s2. And then we go down to the F block and we count over 1, 2, 3, 4. So this is F4. And for the F block, the shell is period minus 2. Well, it's the 7th period, so this is 5F4. Okay, and if I go back and I look at my handy-dandy cheat sheet here, oh, I got to go down to 7s. I'm sorry. So after 7s, you come up here to 5F, then 6D, then 7P. Okay. And so after 7s, I go to 5F, and that's what I found. Okay, so using this trick of electron configurations, of noble gas configurations, and then pairing that with the S block, the P block, the D block, and the F block, mean that you should be able to do electron configurations very, very quickly and very easily. Okay? Now, the last one that I want to talk about is chromium. So here's chromium. And what we would expect for chromium is that we'd be argon. Why don't you pause, see if you can do it, all right? So we start with argon, and then that's 1, 2, 3, 4s2, and then 3d, 1, 2, 3, 4. 3d4. Okay, now there's a problem with this, all right? If I do the orbital notation for this, for just these two orbitals, so I've got my 4s, and it's got 2 electrons in it, and then I've got my 3d, which has 5 orbitals, and I've got 1, 2, 3, 4. Okay, so here's the thing. Elements want to have either a half-filled subshell or a fully filled subshell, like this one. So that's stable. That's close, but it's not quite good. It would rather be either half full, if I could get another electron here, or fully full, which I have no chance of getting to. So what actually happens is this electron right here moves into this orbital, and you end up making this configuration. So this is actually not true. 4s1 3d5. Okay, 4s1, 3d5. Okay, so that's interesting. So that can happen here, and it can happen in a couple other places. I'm going to ask you some questions about that in a little bit. But those are all the kind of last-minute details for electron configurations. You're now ready, or after working on this a little bit more, you should be ready to answer some questions on a test about this.